First, we are going to see the solution of theoretical questions. For question 3rd, in a semiconductor, if the Fermi energy level lies in the conduction band, then the semiconductor is known as degenerate n-type semiconductor. For an intrinsic semiconductor at temperature 0 Kelvin, which of the following statement is true? All energy states in the valence band are filled with electrons and all energy states in the conduction band are empty of electrons. This statement is true. For the first question, we know that boron is a p-type impurity, and you can also see that doping concentration is provided 4 into 10 raised to the power 17 per centimeter cube. Intrinsic carrier concentration is provided 1.5 into 10 raised to the power 10 per centimeter cube. Also, we have a formula for finding the hole concentration, which is we can assume the hole concentration to be approximately equal to acceptor concentration. Therefore, we can write rearranging this equation, we can also write now you have to simply put the values. After solving, you will find that the Fermi level is approximately 0.427 electron volt below the intrinsic Fermi level. So, the C option is correct. For second question, we know that energy of the radiation should be greater than band gap energy, and also energy E is inversely proportional to wavelength. So, the wavelength of the radiation should be equal to or less than the cut-off wavelength, which is provided by 1.24 divided by band gap energy in electron volt, and the unit of wavelength will be micrometer. So, the wavelength should be smaller than or equal to 0.87 micrometer. You can see from the options also that only the A option is valid, as in all the other options wavelength greater than 0.87 micrometer is also in the range, but this is not valid. Therefore, A option is correct. For the fifth question, we have hole concentration to be equal to 1.5 N. By mass action law, we can write electron concentration to be equal to square of intrinsic carrier concentration divided by hole concentration, which will give the electron concentration to be equal to intrinsic carrier concentration N divided by 1.5. Now we are supposed to find the ratio of electron to hole mobility for equal hole and electron drift current. If electron drift current is equal to hole drift current, then remember that here N is the electron concentration, not the intrinsic carrier concentration as is provided in the question. We usually use N to represent the electron concentration, that's why we have used. But in the question, N is representing intrinsic carrier concentration. Don't get confused. We got the hole concentration to be equal to 1.5 N and the electron concentration to be equal to intrinsic carrier concentration divided by 1.5. Now, after solving, you will find the ratio of mobility of electron to hole to be equal to 2.25. For question 6, we have EF minus EV equal to 0.35 electron volt effective density of states in balance band to be equal to 10 raised to the power 19 per centimeter cube. We have a formula for finding the Hole concentration, which can be written as now. The important point that you have to remember is the effective density of states is provided at 300 Kelvin, but we are supposed to find the Hole concentration at 400 Kelvin. So the effective density of states in balance band will change, and you also know that effective density of states is proportional to temperature raised to the power 3 by 2. So the Hole concentration can be written as now. Putting the value of effective density of states at 300 Kelvin, we will get now you have to simply solve this expression, and after solving you will find the Hole concentration to be equal to approximately 63.43 into 10 raised to the power 13 per centimeter cube. For question 7, the concentration profile of minority carriers can be represented as here. This point is representing thermal equilibrium free electron concentration, and this represents the excess free electron concentration at the surface which is illuminated with a laser. You can also see that N naught is equal to 10 raised to the power 20 divided by 10 raised to the power 17. We have used simply the mass action law, and after solving you will find the free electron concentration to be equal to 10 raised to the power 3 per centimeter cube. So you can see that excess electron concentration is significantly greater than thermal equilibrium free electron concentration, and we have studied the formula for finding excess electron concentration to be like this. Now you simply have to put the values. Delta N is provided 10 raised to the power 14. We are supposed to find the concentration at 2 micrometer, so X will be equal to 2 micrometer. Diffusion length of hole is also provided equal to 2 micrometer. Therefore, free electron concentration at X equal to 2 micrometer will be equal to 1 upon E into 10 raised to the power 14. So, the answer will be approximately equal to 0.37 into 10 raised to the power 14. So, the first option is correct.